at the two laboratory points, indicated by the solid Eulerian vectors. The amount of the change will be easier to see if we attach the Lagrangian vector to the left-hand laboratory point, taking as our initial or tagging time the time when the material point passes that laboratory point. The difference between the Eulerian vector and the Lagrangian vector at the left-hand point gives at each instant the change that the material point has experienced. The total change when it arrives at the right-hand point, a vector distance delta r away after a time delta t, can be written as the vector distance traveled times the gradient of the velocity. The distance traveled is just the time difference times the velocity. Now, if the velocity of the entire flow changes with time, as it does here, the Eulerian vectors also change with time. The amount of change will be easier to see if, in addition to placing the Lagrangian vector at the left-hand point, we include as a dashed vector the initial value of the left-hand Eulerian vector. Now, when the material point has arrived at the right-hand laboratory point, the total change it has experienced is given by the difference between the dashed vector and the Lagrangian vector. But this can be broken into two parts. The difference between the velocities at the left and right-hand laboratory points at this instant is given by the difference between the Eulerian and Lagrangian vectors on the left. The change each laboratory point has undergone during this time is given by the difference between the dashed and Eulerian vector on the left. The spatial velocity difference can be written as before as the time difference times the velocity times the gradient of the velocity. The temporal velocity difference can be written as the time difference times the rate of change with time at a laboratory point. To find the total change, we must vectorially add the two effects. The material or substantial derivative is just the expression multiplying the time difference. This is the rate of change seen by the material point as it passes a laboratory point, written in laboratory coordinates. In this way, the acceleration, more simply written in a Lagrangian description, has been expressed in Eulerian notation. To summarize what we have seen, we can tag the material points in a flow by using their locations at some reference time, and then give their displacement, velocity, and acceleration as functions of time and initial position. This is called a Lagrangian description. Alternatively, we can define a coordinate system arbitrarily and probe to find the displacement, velocity, and acceleration at points fixed in that system. This is called an Eulerian description. This has the advantage that it is sometimes possible to find a system in which the flow is steady. It is also mathematically enormously more convenient. We nearly always write the conservation equations for a continuum in this Eulerian system. It has the disadvantage that we're not always referring to the same material point. We can, however, transform from one system to the other by using the fact that displacement and velocity at a laboratory point is the displacement and velocity of the material point that happens to be there. To express in Eulerian field variables the change experienced by a material point, we must take account not only of the change with time of properties at a fixed point, but also of the change of properties with position at a fixed time.